Okay. Oh, yeah. This is, you can read this, how to do well. Um, like I said, you can do this two routes. Either do the work or cheat and not get caught. Right? Okay. Got that. Okay. I forget what the joke was on that. Probably about people who weren't paying attention in class or something like that, and why they're not going to do well. But anyway, this. Let's see, where is that? Oh, here we go. Good. Okay. Anybody? What is science? Anybody? I don't care. Oh, by the way, I don't care if you're right or wrong. I really don't. Sometimes it's better to be wrong. By the way, when I went back to school, after being a film editor, I didn't know much, and I knew I didn't know much. But I quickly learned that most of the other students didn't know much either, and they had stayed that way by not asking any questions, because they didn't want to look stupid, especially when I got into grad school. I knew more then, but I still didn't know very much. And so people just went along thinking they knew stuff, but they didn't, because they didn't ask any questions because they were worried about, whether they looked smart or not. And it gets worse and worse the further along in school you get, until you're finally going for a PhD or becoming a physician, something like that. No one wants to look dumb, but it's actually, if you actually raise your hand and say, I don't understand, usually the thing that confuses you is the same thing that's confusing everybody else, but they've been too afraid to ask. So, since I was not bashful, I stuck my hand up all the time and asked really stupid questions. And it turns out everybody else in the class was wondering those same things, and they had been for the last couple of years. So they learned something inadvertently from me, because I just didn't know. And in fact, that's why you actually do science, by the way, to figure out things. Okay, but anyway, I want a definition. Anybody, a definition of science? Okay. Yeah.
A study of a topic or something like that.
Okay. Oh, come on. Yeah, okay. Oh, I know. In particular, anything?
Honestly, because I feel like there's so many different types of science and fields.
Okay. How about just the natural study of the universe, of the natural world? Okay. Okay. Now, that's actually, what that is not a definition of science. It's a definition, one of the reasons why we might want to do science. Just try to figure out what the hell's going on all around us. There's different ways of of knowledge, of gaining knowledge. It's called this epistemology. We've got the humanities. We've got art. We've got business, let's say, learning specific things that you get good at that you can, let's say, make money. A lot of the reasons we do gain knowledge is for practical reasons, right? But science itself is not really about gaining facts. Science is actually just a process. That's all it is. Scientific okay, scientific method. So science really is all it is a process. It's not one of the reasons we do it is to find out about things, a reliable way of finding out about things in the universe, but it's not just about gaining facts. It's a way to understand things. And like I said, in science we never prove anything. We just say something is more likely than another. And we do that by the scientific method. Now most people, it says here, a systematic enterprise. That means kind of with rigor, doing things in a certain framework, not just all over the place. That an enterprise that builds and organizes knowledge in the form of testable explanations and predictions about the universe. Now, the important part of that testable explanations and predictions. Okay? Now, that's part of the scientific method. You probably think about science in terms of doing experiments. And that's one thing that we do in science. But sometimes, actually, you can't do experiments. Like in evolution, you can do some experiments, but you can't really do long-term. Like, we're on this earth, it's an incredibly short period of time. We basically usually do not get a chance to see any major changes that happen during the Earth's history. The Earth was formed along with the other planets 4.5 billion years ago. It's a number you can't even imagine. We can't even imagine 1,000 years, and yet 1,000 years in geological time is a blink. So there's a lot of things that we would like to do as scientists that we can't. Like, we make predictions in terms of evolution about evolution by natural selection, things, organisms, populations evolve in response to their environment and how the environment changes. The environment is a big thing. It's abiotic, temperature, air, the amount of light, all that kind of stuff, and biotic. All the other organisms that are living. And in fact, probably the most important environment for you guys right now is a social environment. Well, for most humans. We have to navigate all kinds of things as we're growing up and then becoming adults. And it's mainly has to do with reading other people and knowing who you can rely on and who you can't. So, like, now I know that I have a friend in here named Pat, right? You might want to talk to him afterwards. He might be your friend too. Now, but we can't, let's say, one cool experiment would be to take the Earth, run it back in time, and then watch it go forward in time. And we would make predictions about how life might evolve. Not specifically that there would be dinosaurs or at the end there'd be humans or anything like that. Just in terms of what evolution by natural selection predicts in terms of theoretical stuff. It would be really cool to do that, but we can't. So we're kind of stuck. Also, we wouldn't do just one Earth. We'd probably replicate it about 1,000 times. We take 1,000 Earths, make it everything identical, and then there's always a bit of stochastic or random things going on, and see if all the different Earths wouldn't evolve the same things in time, but they would show evolution that might all share similar features. So that would be a neat experiment to do. But we can't always do experiments. So the process, the scientific method, is usually a way of thinking more than anything. And everybody wants to know if they're right or not. And we have what's called beliefs. Yeah, let's get back to that. Beliefs are kind of a shortcut about the knowledge of the universe. It doesn't mean that they're right or wrong. They're beliefs, but they're usually unsubstantiated. Now, doing science is not like a belief. With science, you actually have some idea about whether you're more right or less right. So you come up with, let's say you see something. The sun rises in the morning, goes across the sky, and sets. And you think, why? And then the moon does it, and the stars come out, right? The whole bit. People wonder why it happens, and people have been wondering that for a long, long time. Now remember, there was a point where everybody who was living from that time and before believed that the Earth was the center of the universe. In fact, it's completely understandable. If you didn't know better, you would say, oh yeah, yep, we're the center of the universe, everything seems to revolve around us. Our intuition would tell us that. Now, but a scientist would say, okay, well that's a hypothesis. Is that really the case? Now we know it's not. So we have to test these things, but we can do it just thinking about it, or we can do it by running experiments. Sometimes we can't. So I'll give you an example, another one. It's pretty good. The scientific method, right? Gravity. How come we don't fly off into space? By the way, that's what Newton, the guy who first came up with the law of gravity, asked. He was asking, why does the apple fall to the ground? He wasn't asking that. He was asking, why does the apple not fly off any other old way? So that's where he got his first idea. But let's say, okay, boom, gravity. Okay, so why does this happen? Once upon a time in California, you know how we're full of crazy cults? People believe all sorts of crazy stuff. There were some people who believed that there were these people in the center. The earth was hollow, and people were actually living inside the earth. It wasn't all rock and an iron core and all that. And that these people actually had metal heads, and that because of that, things stayed on the ground. Right? Boom. Okay. You say that, okay. That's a valid hypothesis, explanation, isn't it? It's a matter of, can we test it or not? Can we actually test that hypothesis? Well, we could, drill in to the earth. But we wouldn't even need to do that, actually. All we really have to do is, okay, what are these keys made of? Metal, okay? Now, if it's true that everything stays on the ground because of these metal-headed people at the center of the earth, then the prediction is only metal should stay on the ground, everything else should fly up. We just disproved that prediction. So, now there may still be people at the center of the earth. We haven't really answered that question. But we can certainly say that gravity is not because of people with metal heads or anything else in the center of the universe, because if it was metallic, it would be only affecting metal and not other things. What we've done is we've falsified a prediction. Now that's all that science really does. Now I'm going to leave you with that. That's where we'll pick up. But we don't go around proving stuff. We go around actually disproving stuff like I just did. Religion class or anything, okay? But
you may ask yourself, how do I work this? You may ask yourself, where is that Lord's automobile? You may tell yourself, this is not my
but I mentioned it last class about if you woke up in the morning, you didn't know anything about where you were, who you were, whatever. And you wake up and there's this water flowing past the river from these mountains in the east. And there's a kind of like a garden spot. Lots of plants. There's fruit trees and like an apple tree. And you wake up and all of a sudden you look up and you think, see this big orb rising in the east. And you go, I wonder what that is. You don't know. Remember, you don't know this. And it goes all the way across the sky. And then it sets in the west, and then the stars come out, and if you follow a star, you realize that the same thing happens. It goes across the sky, and it sets, the moon comes up, sort of thing, and over a couple of days, you realize the same thing happens all the time. Where would, in terms of where you are, what would you think? In terms of everything else that you've seen in sky and all that. You ready? Like, yeah, the center of the universe, as far as you know. And it's actually intuitive, right? Sure seems that way. Remember, forget about Copernicus or Kepler or Newton or any of those. This is kind of prehistory or ancient history, when people didn't know anything about solar systems and all that. And, oh, by the way, I mentioned there's an apple tree. Somehow, you wake up and a new person then shows up. So there's two of you, and one eats the apple and gets the other one to eat the apple, and there's, suddenly there's knowledge, and you get thrown out of the garden, and you're at the mercy of tyrannosaurus. So, that seems like the universe you're in, and let's say 600 years ago, that's what everybody believed, or 600 years ago, and before that, everybody believed kind of that sort of idea of where they were. There were different origin stories with different cultures, of course. The Hopis, they believed the ant people went underground, and then when they came out, those were the basis for the Hopi Pueblo people that still exist in Arizona. There's many other origin stories. But it wasn't until later that, or till Copernicus came along. He's Polish. This was right around the time of the Reformation. In Europe, the big schism between Catholicism and Protestantism. And he imagined that, well, maybe he had some evidence, and he proposed a new theory, which was that the sun is the center of the solar system, and all the planets revolve around it. But it was not some great revelation to him. In fact, he proposed it, and he said it could be this way. It wasn't like this is really how it is. The thing is that system that he developed, it didn't make celestial predictions any better than the one before, where the Earth was the center of the universe. Mainly because he imagined that the planets had circular orbits and not elliptical orbits, and that makes a big difference in your calculations. And then later on, Kepler stated the laws of planetary motion. Galileo, with his telescopes, actually showed that other planets had objects circling around them. He got thrown in jail or house arrest for the last 16 years of his life for believing that by the Catholic Church. But eventually, they stopped burning people at the stake after about 100 years of believing, that the Earth was not the center of the universe. Now, in terms of knowledge, the fact that most people, let's say, believe a certain thing does not make it true. Because as I just mentioned, back then, everybody before that time believed that the Earth was the center of the universe. There were some problems, of course, with it because the planets wander. That's what the name planet mean in, I guess it was Greek or Latin, means wandering. So it wasn't, planets don't go across the sky like stars and galaxies that are much further away. But anyway, eventually we came to know that through many, many years, that there is a sun, we have a solar system, there are many solar systems in the Milky Way. The Milky Way is one of billions and billions of galaxies, each which contain billions and billions of stars, and other solar systems, some of which are like our own and most which aren't. And now we're living supposedly in an expanding universe. But in terms of knowledge, it was slowly over time, we got a better picture of the universe, at least as it appears to be. Now, like I mentioned earlier, we can't prove anything in science, but we can make calculations in regard to likelihood, how likely something actually is. And so we're going to discuss a little bit about what science is and does and how it actually operates. And most of you, as I mentioned, probably think it's about experiments, but sometimes you can't do experiments. But it doesn't mean that you can't use the conceptual framework of the scientific method in your studies of the universe. And in fact, most of you do science all the time. You use evidence for making decisions about your life, whether it's from, how many people here commute from far away? Okay. Which routes do you take? That's a question that you can ask. What's the fastest route to school? As you know, now maybe you take the same route because that's the route you were taught. Or you take the freeway all the time because you think that's the fastest, whatever it is. Let's say it's a legacy. Or, in fact, you think about it and you think, well, at certain times of the day I'm going to take one route and not another because the freeways might be, stop and go, and you'll be there for the rest of the day trying to get to school. So we all do science in one sense or another. Let's say the clothes we pick to wear. We use many reasons for picking the clothes we wear. Some has to do with how we want to look. Others have to do with, let's say, the weather that's outside. And you can decide about the weather. You can get evidence either from online or looking outside, feeling how cold it is in the morning, about what clothes you want to wear. You may decide that you want to look good no matter what, so you'll dress in something that makes you look really good, but you'll freeze to death during the day, but that's besides the point. Oh, so we kind of discussed this. So why do we do science, anybody? What do you think? Prove a point. Prove a point? Okay. Glasses. Anybody else?
We will explain things that we couldn't explain in the past.
Okay. Anybody else? Yeah.
To disprove a claim.
Disprove a claim. Okay. What about practical reasons? Anything? We do a lot of science nowadays. In fact, most people justify doing science because of practical applications. So like biomedical science, right? Now, everything that we do does not mean that we do it just for practical applications. We do a lot of what's called basic science, where we just want to essentially find out what the hell's going on. It's a pretty good way of discovering knowledge, reliable knowledge. Doesn't mean that it's proven, but it's likely, and it's provisional in terms of what we know at a certain period of time. So, kind of like explaining phenomenon, but we just want to know what the hell is going on. Okay. Like I mentioned, there's other ways of gaining knowledge in the world. We have all these, take history. And as I mentioned earlier, you can actually take the scientific method and apply it to anything, really, that you want in terms of trying to gain reliable knowledge. The nice thing about science is it's generally self-correcting. So even if you wander down a rabbit hole, eventually you'll find your way out, or someone else will, and you realize that the last 50 years, what you thought was completely untrue. So when I took out my keys and dropped them and said there were people living inside the earth with metal heads and that was the cause of gravity, that's a hypothesis, what we call a hypothesis. And you can test that and you can disprove it. In fact, you can disprove it without even doing an experiment. Not about whether there's people in the center of the earth, but whether that's the cause of gravity. Because obviously, if that was the case, metal would be the only thing that's sitting on the ground and everything else would be flying off into space. Okay. Now, as far as, oh, good. Oh, that's not what I want. Now let's see, where is he? No, I don't like that one. Salute.
Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we so don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guess is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience. Compare it directly with observation to see if it works. If it disagrees with experiment, It's wrong. In that simple statement is the key to science.
What?
It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are, who made the
Oh, I
guess,
don't.
or what his name is. If it disagrees with experiment,
I'll, next
wrong.
time I'll,
That's all there is to it.
sorry about that. Okay,
Guess,
what?
find the consequences of it. What was it, like third party he said? It was guess, or find the consequences.
Okay, so, what you do is, you, come up with an explanation. It can be a crazy explanation, like I just mentioned about the keys and all that. And, then you compute what he said the consequences, or you say this explanation makes certain predictions that you test. Now, this is Richard Feynman. He was a Nobel Prize winning physicist who was at Caltech out in Pasadena. He died prematurely from cancer. But he was brilliant. He worked on the Manhattan Project when he was like, the Manhattan Project was to build the first atomic weapon during World War II, because we were afraid the Germans were going to beat us to it. He was like 19 years old, so he was a genius. So he's talking here about science. So physics makes very, very, very specific predictions. Like I mentioned, theory of gravity, Einstein's theory of general relativity, made predictions about the fact that light would be bent as it passed, let's say, by the sun or by any other large object with mass that would create a gravitational field. And light itself doesn't have mass, but it's energy, and we know that from Einstein that energy equals mass times the speed of light squared, so you can compute either one. They're essentially equivalent things. You may think, well, this seems different than energy, but you can convert it into energy. So, and of course, those predictions were first tested by traveling to a solar eclipse where the sun is blotted out by the moon, and doesn't last very long. But according to Einstein's theory, you should see the light from other stars passing by the orb of the sun bent by a certain amount, a very specific amount. And there were a bunch of other things that Einstein's theory of general relativity predictions that it made. The latest one was this gravitational wave business that was recently confirmed. Took that long to actually design an experiment that would detect gravitational waves. Okay, so the thing about what he just said, I should probably just do it again.
Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we so don't laugh, that's really true. Then we compute the consequences of the guess.
Predictions?
To see what, if this is right, if this law that we guess is right, we see what it would imply. And then we compare those computation results to nature. Or we say compare to experiment or experience. Compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. In that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
So, that is the key to science. And that's why we can gain reliable knowledge with science. For that very reason, that we can show that something is actually wrong, and then we can go on and try to find another explanation that better describes that phenomenon. Doesn't mean that explanation is right. As I mentioned, Newton's theory of gravity stood for 300 years, and we still use it in terms of our computations for planetary motion in our solar system and sending up spacecraft and all that. But the new theory in town from 1915 is Einstein's theory of general relativity, and that's the current theory of gravity. And it's likely that that will eventually be replaced with an even better, more explanatory theory in the future, but it's hard to know. Right now there's kind of a discrepancy between the very, very small quantum, like what are atoms made of, the different particles that are made, protons and neutrons are then also made of quarks and with different colors and all kinds of crazy stuff. And then gravity, because gravity happens at a very, very large scale, and everything else happens, like the electromagnetic force, at a very, very small scale. And how do you marry those two things together? But anyway, that's what science kind of does. And therefore, to actually do science, aside from coming up with an explanation, determining what the predictions are for that explanation, and then testing it, you need a falsifiable hypothesis. That means you can disprove something, right? If you can disprove something, then it's a scientific hypothesis or a scientific theory. If you can't, let's say you come up with a supernatural explanation or a moral explanation, like taking echinacea prevents colds because it gives you better morals or something like that. Okay, you can't really test that. I guess you could, but you could quickly disprove it. But in general, that's the basis, the structure of so let's take a look at the scientific method per se. Now, let's see here. Okay. Usually, we start with an observation. We look around and we're curious whether it's about the best way to get to school or what clothes to wear or some other weighty thing about whether, is the climate changing, is the earth warming, and why is that happening? And then we come up with a question. Why is something that we see or observe happening? And then we come up with an explanation, and that's what's called a hypothesis. So if we start out with the car won't start, we ask, why doesn't the car start? The car won't start because the battery is dead is an explanation. That's a hypothesis. Another explanation is there's no gas in the car. Now, if it's a dead battery, one of the predictions that you would make is that if you turn the key, the starter motor should not kick in because there's not enough energy to run it. If it was, let's say, gas, you would say, well, I could differentiate between no gas and a dead battery, because if there's a battery, you can still get the starter motor using the electricity from the battery, to turn over the engine, but it won't start, so we can discard the battery hypothesis right off the bat. If you really want to test it, though, you would replace the battery and see what happens. Okay? Now, so that's the prediction is the hypothesis is true, and you replace the battery. You do an experiment in this case. The car should start right up. Obviously, you can falsify that. You can do the experiment, and if the car still won't start, you can say, oh, it's not the battery. Now we can go on to another explanation. There's a whole bunch of, let's say the alternator is broken or something like that. The fuel injection system isn't working. You parked your car in the garage, but you have rats and they crawled into the engine compartment, and rodents love the taste of the plastic surrounding wires, and they like to chew that up. And so maybe that's the explanation. You shouldn't laugh at that one, because that actually happened to me. So it wasn't the battery, it wasn't the gas, it was the goddamn rats. In fact, if you ever went, I don't know if any of you like to go like hiking or backpacking in the Sierras, but if you go up to an area called Mineral King, which is east of Fresno in the Sierra Nevada, it's high country. They have these rodents, very large rodents called marmots. And marmots, like other rodents, like to do the same thing. They actually have signs that say, you know, make sure your engine compartment is secure, because they'll get in there and chew up your wiring. Okay? Now, then we test the hypothesis, or we actually test the prediction with an experiment, or we can just, let's say, like I said, with an observation. Let's say you don't even need an experiment. If it was actually not the battery, let's say it was something else, then the battery should still be able to get the engine to turn over in terms of the starter motor. Of course, it could be the starter motor, too. Now, once you do that, and you say, oh, it's the battery, then you can stop there. But it may be that it's not the battery. And so, generally what you do is go up here and you propose a new hypothesis. It makes different predictions, and then you follow it again. Now, oftentimes in science, we don't just look at one hypothesis, one explanation. Sometimes we compare a series of hypotheses that might be related. So there might be a series of different causes that, let's say, aren't mutually exclusive. Let's see. Okay. Let me give an example. In evolution, there's something called, when we study it, there's something called sexual selection. Now, mostly when we talk about evolution, we talk about survival. Who survives and who doesn't. But a lot of success in terms of evolutionary success in fitness, the successful are the ones that get to mate and produce offspring. And so, oh God, that's not good. Okay, we'll see what happens. It's not good at all. Okay. So, well, that's one explanation for, let's say, why an organism has higher fitness than another, or it might be, the other hypothesis is that one organism lives longer and can then, therefore, have more sex and more offspring. They both might actually be right. In fact, in terms of evolutionary fitness, that's exactly what it is. It's the number, how long you survive and how many offspring you can produce. Ultimately, it's the number of offspring. Even if you don't survive as long as someone else, you still might produce a far more number of offspring because, let's say, in terms of sexual selection, you're more attractive to the other sex or something like that. Okay. Now, the key here for a scientific hypothesis is it falsifiable? In other words, can you prove it wrong? Not can you prove it right? When we test something, we test it with as much rigor as possible. That means, let's say I come up with a hypothesis and I love it, and I'm sure it's true. And I'm going to go out there and I'm going to gather as much evidence in support of that hypothesis. That's not what we do. We take that favorite hypothesis and we try to blow it up. We may start out with a pea shooter and then go to an M16 and then to a howitzer and then eventually nuclear weapons. And if we can blow it up, that means we falsify it. That means it's wrong. And we just learned something. It's a great thing about being wrong. You can learn something. Because if you think you know something, that's usually when you stop asking questions. A lot of people like answers. Other people like questions more. So when you can show that something is wrong, it's actually great. I've proved myself wrong many times. You may think, oh God, how depressing. I didn't look at it that way. For an example, I talked about seed dispersal by animals, and I was looking at rodents that bury seeds all over the place and have a very good spatial memory to remember where they are. And in the literature, it said that ground squirrels didn't do this strategy. Ground squirrels are usually bigger than little tiny mice, and so according to the literature, they put most of their seeds all in their burrow in one location. So I thought, well, they're probably not very good dispersers of this plant of the seeds that I'm interested in. But I didn't know this for sure. I couldn't just assume it from the literature. Literature can be wrong. So I went out and I tested it. I built this big enclosure, 10 meters on a side. I took a bunch of these seeds. They're called desert peach. They're kind of like an almond. They're a little more, well, wild almonds, it turns out, are kind of bitter because of cyanide in them. And these are the same way. But they still taste pretty good. I radio labeled them with a radioactive element. And then I put them out in this box inside the enclosure, and I also put an animal in there. different species of animals. I put kangaroo rats, I put deer mice, I put chipmunks, all kinds of different things, including ground squirrel. And lo and behold, it turns out that the literature was all wrong about ground squirrels. I was happy about that because it seemed like ground squirrels took all the nuts from this plant. And if, in fact, they had ever put everything into a burrow, it wouldn't have mattered in terms of how good of a disperser they actually were. So we look for falsifiable evidence, or we try to falsify something. A scientific theory is a well-substantiated explanation of some aspect of the natural world or some natural phenomenon based on the body of facts. Now, we can't prove anything as an absolute fact, but on the evidence that we have that has been repeatedly confirmed through observation and experiment, or repeatedly tested and not falsified. Such fact-supported theories are not speculation. In other words, they're not just an opinion or a conjecture with no evidence whatsoever. But kind of reliable accounts of the world that make very specific predictions. So Einstein's theory of relativity, it's a theory of gravity. There's a bunch of different hypotheses that make up the theory of gravity, or like evolution, there's a ton of different hypotheses for different aspects of the theory. But the theory overall explains what we see in terms of life on this planet and how it might have changed. It is a factual explanation, but it's provisional. If new evidence comes along that seems to refute or disprove, then we either toss it, we say, oh, it was a beautiful theory, like Feynman said, it was a gorgeous theory or a gorgeous hypothesis, or we modify it. So, like Newton's theory of gravity, it was wrong. Einstein disproved it. It's actually still useful, so we still kind of use it, but Einstein's theory of relativity was so revolutionary that it replaced Newtonian physics, essentially. Also, a theory usually has to do with some larger phenomenon, not a specific causal mechanism. So some larger phenomenon like, let's say, gravity, or let's say evolution. And then there's different hypotheses that make up that overall theoretical construct. What's a theory? Huh? What's a theory? Anybody?
Educated guess.
Okay. Educated guess. So, in other words, it's kind of like the same thing as a hypothesis. Is that right? Okay. Yeah.
I feel like it's something that hasn't yet been tested or proven
Okay.
wrong or proven right.
Okay. So this is kind of like an opinion?
Yeah.
Okay. Anything else? What do you think a theory is? I know you're in the back, so you can escape these questions, but in the red, yeah.
I would also say it would be an educated guess, because it kind of goes hand in hand with the hypothesis.
Mm-hmm.
I would say it's an educated guess.
Okay. Good. Anything, yeah.
Well, a theory is something that has been tested, but you can't really prove, like you said, you can't say it's false, and you can't say it's true.
Yeah.
So theory is something that's been tested, but it's legitimate, like, makes sense that people can use to further, make tests on or.
Okay.
Right.
Do you think it's kind of like, it could be true or could not be true, or is it likely that it's true?
It's likely that it's true, but you can't.
Okay, exactly. Okay, that's good. Okay. So, there's a difference between number 2 and number 3. Number 2 is an opinion. We often hear people say, let's say something about, let's say evolution, but that's the current one, or global warming, or something like that. It's only a theory. That is not a theory in terms of a scientific test or a scientific theory. A scientific theory is a completely different animal. Has nothing to do, well, it might start out as a guess or an opinion, but a theory is more like the third one, where provisionally this is the best explanation that we have at a given time. Now, you're probably wondering, well, what's the difference between a theory and a hypothesis? Okay. So, if you actually look at the bottom here, oh, a model, by the way, is the same thing as a hypothesis. Whether the model is a model airplane that still works on the fluid dynamics of flying, or whether it's a model, a mathematical model. Same thing as a hypothesis. Mathematical hypotheses or models, you can test them because, very specifically, because they make very specific quantitative predictions. But even if a theory fails, one prediction is falsified, then there's a question about whether the theory is valid or not. And in fact, Newtonian theory of gravity makes some predictions that are not borne out, that only are explained by Einstein's theory of general relativity. So, oh, that's right. One of the predictions, or one of the, predictions of Einstein's actual special theory of relativity, which was done earlier, was that the universe's speed limit is the speed of light, 186,000 miles per second. Seems like pretty fast. If you're going that fast, you would probably, all the hair from your body would be ripped off and all your flesh. And so it's fast, but it's actually, in terms of space travel, it's very, very slow. That's why we say that something is, let's say, 100 light years away. It would take the speed of light 100 years to get there. So when we look at stars, or we look at the moon, the light from the moon, we're not actually seeing the moon or the stars at present time. We're seeing it back in the past, depending on how far away that is. Takes 8 minutes for the light from the sun to get to the Earth. The most distant objects, in other words, the most furthest back in time, that we can see are about 13 billion years old. A couple of 100 million years after the universe was first created. Some physicists, they tested the speed of light business. It turns out you can actually make the light go slower. They've done a whole bunch of experiments with that by using magnets and things, but that's not important. The thing is, it states that you can't go faster than the speed of light because time is not constant, but you would actually have to go back in time. And according to current observation theories, we can't do that. Is science robust? That means, is it strong? Is it reliable? Even if you have some explanations that's incorrect. Yeah, and it's because we can falsify things. We can prove they're wrong. So, a good example is there was anybody in here ever have an ulcer? Okay. It was thought that most ulcers are the result of stress. You know how you have a big test and you're stressing out and your stomach feels terrible and kind of acidic and and there's a lot of acid in the stomach. And so it was thought that maybe stress was the reason for most ulcers. Well, there was this physician in Australia, and at the time it was thought that the stomach is so acidic that microorganisms can't live in that environment. Well, that was an assumption that hadn't really been properly tested. And when he was investigating ulcers, he kept coming across this bacteria, and he thought, well, maybe that's actually the cause of a lot of ulcers. And, okay, so how do you test it? Well, you can test it on animals. You can test it on people, but of course, there's ethics involved. Isn't that a bummer? You just can't give people this bacteria, but he did the next best thing. He gave himself he took a draught of a big amount of fluid full of bacteria, drank it down, immediately got a terrible case of gastritis, which is usually a precursor to getting ulcers. And so we actually showed that, in fact, it wasn't in people's heads that they were getting ulcers because they were anxious and stress-ridden, but in a lot of cases there was actual infectious agent that was causing that. The stress hypothesis had been in existence for years, like 50, 100 years. People had believed it. It was incorrect. But eventually, some guy came along and decided to actually test it. So even if I go out and want to confirm, let's say, an explanation, a hypothesis that I make, and I collect all the data that shows it's true, there's always usually going to be some other scientist out there who's a dirty bastard and is going to try to prove me wrong. And I don't like to be wrong. But he can publish his results, he can test it, and he can actually show that, oh, I'm wrong. I might have staked my reputation on it, but it won't matter, because there is something called objective reality, despite what you've heard from the current occupants of the White House. There is not an alt reality. That's why if you're interested in the stars and the cosmos, you don't study astrology, you study astronomy. If you want to be a doctor, you don't study to be a witch doctor. A lot of people still use witch doctors, whatever they're called. Usually we call them quacks. Quack, quack. So like they come along with a great, you can always hear about these things that a lot of people now think marijuana will cure everything. And they're right. It will, in your mind. Okay, so, but I want you to understand that even though people can be misinformed because they just don't know, it hasn't been tested yet, that there's a better explanation out there. Even if something is incorrect and has been written about that way for a long time, it can still be corrected, and that's usually what science does. There have been, before there was a theory of the germ theory of disease, there were all these other explanations. It was called the humoral explanation. There were 4 types of substances, and they had to be right balanced in the body. This came back from Roman times. And that's why people used to bleed. Barbers would bleed people because they thought they were going to rebalance the humors. And oftentimes that, when they did that, they ended up killing the person. But eventually, a new theory was born, germ theory of disease from observation with microscopes. I think that's good for now. Like I said, I'll have everything up. Fortunately, this lasted long enough.